trying to get rid of that. But okay, anybody have any questions from last time? We're going to start out with another example of a principal stress problem. Okay. So let's say you have a stress tensor that's equal to 190,910,000 megapascals. Okay, that stress represents a single point in a material. And we want to do these things. Calculate the principal stresses. Maximum to minimum. Second, what is a principal stress tensor and draw the corresponding coordinate system. And then third, rotate the coordinate system positive 45 degrees about the axis for the middle principal stress. Okay, so why would we do that? That seems like unnecessary busy work or whatever. Rotate 45 degrees about the axis corresponding to the middle principal stress. But in fact, this is a really important thing. When you find that principal stress tensor, and then you transform that stress into a new coordinate system rotated, it could be plus or minus 45 degrees actually, but about the middle axis, the axis corresponding to the middle principal stress, that gives you a coordinate system with the maximum absolute value of shear stress. So that's, if you have a material that's especially susceptible to fracture in shear, like brittle materials are, then this coordinate system will tell you how likely you are to have fracture. So this is going to show us the maximum absolute value of shear stress. It turns out there's an easier way to just, if all you want is the maximum absolute value of shear stress, there's an easier way to calculate it, and I'll tell you that. But this is the way to come up with a stress tensor that has that shear stress in it. Okay, so first, let's do it using a calculator. So this is how you do it in a TI-89. So you could go, so first enter this matrix, 190, semicolon, 9, 1, 0, semicolon, 0, 0, 0, and store that somewhere. Let's call it M. Actually, I usually put that in S, so let's let's call that S for stress or sigma. And now go use the command, and this is I think it's eigenVL. This is just, you go to catalog and look for that function of S. And it'll give you the values 10, -8, 0 in squiggly brackets. You're late. And then do the same thing with eigenvectors. That's eigenVC of S. And that will give you the values. It'll give you a matrix 0.7071, 0.7071, 0, then negative 0.7071, I'm reading off the columns here, positive 0.7071, 0, and then 0, 0, 1. And the way to interpret that is the principal stress 10 and the axis, so this 10 and this column gives you an axis. Those are a corresponding pair. So this is an outward-facing normal to a face where this is the traction. This is the normal traction. Then I'll use green. The -8 corresponds to this outward-facing normal. So -8 and the vector negative 0.7071, positive 0.7071, 0. Those are a pair. And then the third pair is 0 and 0, 0, 1. So these are pairs of a principal stress and a corresponding outward-facing normal vector for the stress element. Okay, so what I usually do is, if I'm going to come up with a new coordinate system that corresponds to the principal stress tensor, I try to find, I find which of these vectors is closest to the original coordinate system of 1, 0, 0, 0, 1, 0, 0, 0, 1, and make those the axis. In this case, I guess they're sort of halfway in between, but I'm going to say the new x is 0.7071, 0.7071, 0. The new y-axis is this one, negative 0.7071, positive 0.7071, 0. And the new z-axis is the same as the old z-axis, 0, 0, 1. And so now, if our old coordinate system is this, our new coordinate system has x this way, y this way, and z still this way. And now you have to check and make sure that it obeys the cross product rules for the axes that a coordinate system has to have. So I cross j, you know, the x axis crossed with the y axis needs to give you the z axis. So let's just check all these. I cross j, does that equal k? You can just do this with the right-hand rule. It's a little hard to tell where my vectors are pointing. These two both live totally in the xy plane. And so right-hand rule says x cross y is equal to z, so that's good. Does anyone here have any frickin' idea what I'm talking about? Okay. Is it you, though, or are you assuming it's someone else?
No,
okay, it's you?
I
okay, good.
It was hard at first because I didn't realize that x and y were in the same
Okay, yeah.
thing.
You can see it if you... Yeah. You can see it if you look closely at the components. You can see that they don't have any y component, any z component. Okay, so this one works. And then x cross z equals negative y. So I'll write that as I cross k is equal to negative j. Does that one work? Yeah. And then the last one is j cross k is equal to I. Does that one work? Yeah. Okay, so this is a valid coordinate system, a right-handed coordinate system. And so this is the order that we're, so if this is the order of the coordinate axes, this one, then this one, then this one, then in our principal stress tensor, that's the order that we need to put these values on the diagonal. So this is the x diagonal, y diagonal, z diagonal. Okay. So the stress tensor is 10, 0, 0, 0, negative 8, 0, 0, 0, 0. Question?
So those eigenvalues are our maximum and minimum values.
And then one in between.
Yeah,
Yep.
the maximum and the one in between.
Right.
Which we have.
That's right. And they don't always have to be a positive and a negative. It could be 20 and 15, and those are just the positive, the maximum and minimum. Any other questions? Yeah.
So why did we draw the new coordinate system?
Why did I?
Like, what's the point of that?
I just wanted you to think about that. There's not really any use for that unless you yeah, just for visualization. Right. Yep. Yes?
If we were solving this by hand instead of with a calculator, how do we know which order we should go in?
Okay, so I'm going to do it by hand next. This isn't, so notice this isn't the only way you could do this. You could do any permutation of these three on the diagonal. They would just correspond to different coordinate systems. And all those coordinate systems would just be rotated at 90-degree angles from each other. Okay, so now let's, so what's the middle principal stress? Yep. And that corresponds to the z-axis in this coordinate system, right? You see that, what I'm talking about? It's the 0 is in the z position on the diagonal. So we're going to rotate the coordinate system positive 45 degrees. You could do negative also, about the z-axis. So the rotation matrix is equal to cosine of 45, sine of 45, 0, then negative sine of 45, cosine of 45, 0, 0, 0, 1. So that's 0.7071, 0.7071, 0, negative 0.7071, positive 0.7071, 0, 0, 0, 1. That's the rotation matrix.
Sir,
Mm-hmm.
would it be okay if we did, or is it acceptable as well? Because I get confused sometimes. So, like, I would do QZ to
Mhm.
indicate I'm rotating around the Z.
Yeah. Yeah, sure. I think, what you should do is just program these into your calculator and then,
Yep. But
Okay.
I mean, when I'm handwriting this
yep.
stuff down.
Yeah, that's a reasonable notation. What? Okay. And so then, the stress tensor with the maximum shear stress is equal to Q, that matrix Q, times our principal stress tensor, 10, 0, 0, 0, negative 8, 0, and then 0, 0, 0, times Q transpose, and what you get out of that is 1, negative 9, 0, negative 9, 1, 0, 0, 0, 0. And what that tells you is, in other words, the absolute value of, well, let me write it like this. So the maximum shear stress, tau max, is equal to the absolute value of negative 9, so 9 megapascals. Or another way of saying that is the stress tensor that I gave originally happened to be one where you saw the maximum value of the shear stress. And so you could use this shear stress in a few different, there are some different strategies for determining where a material is going to fracture. But you would plug this value into that criterion, and it would tell you yes or no. In this loading setup that you have, this material is at risk of failure. Okay. You can also, so this is the way to get the stress tensor, but if you only need the value, so if you only need to know the maximum shear stress, which really is usually all you need, you just go the maximum principal stress minus the minimum principal stress divided by 2. So these are the principal stresses. You need to get those principal stresses before you can calculate the maximum shear. So in our case, that would be 10 minus negative 8 divided by 2 is equal to 9 megapascals. And it gives us the same information as using that rotation matrix. Well, it doesn't give us the stress tensor, which you might need for some reason, but it does give us the maximum shear stress. Yep.
What's the difference again between
Shear
shear stress and strain?
stress and shear strain? Or just shear stress and strain in general? Strains are deformations, so they're measurements that tell you how much the material is either stretched or contracted, or how much the angles have changed. Stresses are measures of loading. And so those shear stresses, whenever you get confused about what a stress means, think of the stress element. So those shear stresses are telling you how much traction there is on the face of the stress element going parallel to the face, whereas the normal stresses are perpendicular to the face. So yeah, I think it's really useful to just always think in terms of stress elements. And really, I probably should have. I'll draw out the stress element when we do this by hand. Any other questions? Okay. Let's do this by hand. Check out my new wedding ring. I made it myself. I am an engineer, and so I was like, paper clips bend. I'm going to bend this into the shape of a circle. It just saves me a lot of time, because otherwise there's just like a line of girls always at my door. Okay. So the equation that we need to solve to calculate the principal stresses goes, what's our original one? So here's what we need to solve. 1 minus lambda, then 9, 0. The second row is 9. And then the quantity 1 minus lambda again, 0. And then the last row is 0, 0, minus lambda. And we want a solution where this times a normal vector, a unit vector, is equal to the 0 vector. And so to solve that, it requires that 1 minus lambda quantity 9, 0. Then next row 9, quantity 1 minus lambda 0. And then the last row is 0, 0, minus lambda. We need the determinant of this to be equal to 0. Okay, so the determinant says quantity 1 minus lambda times, all in brackets, the quantity 1 minus lambda times negative lambda minus 0. And then going across the top row, we have minus 9 times, in brackets, 9 times negative lambda minus 0. And then plus 0 times something is equal to 0. So the quantity 1 minus lambda times the quantity negative lambda plus lambda squared minus 81, this is plus 81 lambda, is equal to 0. So that's minus lambda plus lambda squared plus lambda squared minus lambda cubed plus 81 lambda equals 0. So negative lambda cubed plus 2 lambda squared plus 80 lambda is equal to 0. We can factor out 1 lambda. I guess I'll factor out the negative 2 for aesthetics. So negative lambda times the quantity lambda squared minus 2 lambda minus 80 is equal to 0. So we can see that 0 is a root because we factored out that negative lambda. And then for the other two roots, we can use the quadratic formula. And hopefully if you solve that, you get what we got before, unless I made a mistake. I think that looks right. So the other two should be 10 and minus 8. That's from the quadratic formula. Okay, so now one by one we're going to plug these back in to this equation. I'll call this one star. Plug it back into star and solve for the unit normal vector. So now find the corresponding outward facing normals. So I'm going to start with lambda equal 10. So we're going to get, so 1 minus 10, this will be negative 9, this will be negative 9, this will be negative 10. So negative 9, 9, 0, 9, negative 9, 0, 0, 0, negative 10, times nx, ny, nz is equal to zeros. And so we get a first equation that says negative 9nx plus 9ny is equal to 0. A second equation that says positive 9nx minus 9ny is equal to 0. And a third equation that says negative 10nz is equal to 0. These two are redundant. That's just a single equation that says nx is equal to ny. You see that? Okay, so we know that there's no z component. We know those two have to be the same. So pick any, you can pick any value where nx and ny are the same thing and then normalize it, right? Pick nx equals ny equals 50. then you get the vector 50, 50, 50, normalize it, and you'll get 0.7071, 0.7071, 0. It also works with the vector in the exact opposite direction. It always does. So the other possibility is negative 0.7071, negative 0.7071, 0. We can take our pick of those two. And that corresponds to, so this goes with the principal stress of 10. Any questions about that one? Okay, so now let's do it with lambda equal to negative 8. So 1 minus negative 8 is positive 9. Then we have 9, 0. Second row we have 9, positive 9, 0. Third row we have 0, 0, positive 8. Multiply these by nx, ny, and z. And set it equal to the 0 vector. And this gives us 3 equations. The first one says 9nx plus 9ny is equal to 0. The second one says 9nx plus 9ny is equal to 0. And the third one says 8nz is equal to 0. Again, the first two are redundant, give you the same information, and that information is that nx is equal to negative ny this time. This one tells you that nz is equal to 0. And so there's 2 possibilities that meet this requirement. One is negative 0.7071, positive 0.7071, 0. The other one is positive 0.7071, negative 0.7071, and 0. And whichever one of these you choose goes with a principal stress value of negative 8. Now you can go through the same procedure with the 0, or you could just take the cross product of these two. You know the third axis has to be perpendicular. So if you cross the first 2 principal axes, you get 2 possibilities. One is 0, 0, 1. The other one is 0, 0, negative 1. And whichever one of those you choose goes with a principal stress of 0. Yep.
Okay, so you said that we can use either one, the positive or the negative.
Yep.
But if we pick one, do we have to pick the same for the others to make sure that they all cross?
That's right. So the only restriction on which one of these pairs you use is that in the end you're going to pick 3 of them, and then you need to make sure that they meet those requirements for a right-handed coordinate system. And I think all that means is if you if you pick 3 axes at random, and then they fail on the requirements for a coordinate system, just switch one of the axes, just one of them, and then it'll work. I think that's right. But you have to find a set of 3 that work. I think all you have to do is switch one. So so now you just have to, I say find, look, you just have to choose three axes that satisfy the coordinate system requirements, and that's the right-handed coordinate system requirements. And just like we did before, I mean, I'll just write it like we had it before. So we'll choose our new I to be 0.7071, 0.7071, 0. And that goes with the 10. Our new J is negative 0.7071, positive 0.7071, 0. And that goes with negative 8. And then our new K, choose 0, 0, 1. And that goes with 0. So in other words, in the X position of the principal stress tensor, we have the 10. In the Y position, we have the negative 8. And then in the Z position, we have the 0. We could have chosen, we have a whole bunch of options of what to choose as what axis. You just have to, and then if we would have, like, what if we would have chosen, what if we would have chosen this to be our x-axis, this to be our y-axis, and this to be our z-axis? We could have done that. These would have been in a different order in the coordinate system. And then when we do our rotation of 45 degrees to find the stress tensor with the maximum shear stress, we would have just rotated 45 degrees about a different one of those axes. We would have rotated about what we were calling the x-axis. Any questions about that? Okay, so then, and then the rotation is the same to get the maximum shear. Any questions just generally about principal stresses or anything that pop to mind? Yep.
So, why do you keep choosing like sine and cosine of 45? There, like, can't you just use like one negative one?
Okay. So yes, let's. So the we had these requirements, right? We had nx is equal to ny, and we had that nz is equal to 0. Okay. We're going to choose any values of nx, ny, nz that satisfy it. So, for example, say we chose this vector to be equal to negative 50, 0. Okay? But then we need it to be a unit vector. It's an outward-facing normal unit vector. And so to make this a unit vector, well, I shouldn't put this on here. It's just a vector right now. The length of that vector is 50 squared plus 50 squared square root. What do you get? Is that square root of 5,000? And now the unit vector in that direction is negative 50 over square root of 5,000. Negative 50 times the square root of 5, negative 50 divided by the square root of 5,000, 0. And when you do that, you normalize this vector, you get negative 0.7071, negative 0.7071, 0. So that 0.7071 is just what you get when you normalize that vector, make it have a length of 1. Any other questions? So I have one more thing that I want to talk about related to stress. And then we're going to finally get into, so basically we're at the end now of talking about what stress is, how to represent a single state of stress for a point in different coordinate systems, how to find all the maximum values of those stresses given an initial state of stress, and then how to go from that stress to the strain and vice versa. Okay? That's where we are right now. What we haven't done yet at all is figure out how to take an object with a certain set of loads applied to it and figure out what the state of stress is at a point inside that material. Okay? So basically we know a lot about what stress is and what strain is and how to do math to relate those two. But we don't know anything about how to calculate the stress or strain in an actual case. Okay? And so basically after this last thing I talk about, the entire rest of the class is going to be a discussion of how to take, say, a beam under a certain set of external loads and calculate what the stresses are at different points in the beam. Then we'll apply all these things, figure out the principal stresses, the maximum shear stress. But that's basically the entire rest of the class is just figuring out, okay, well, we know all this stuff that we can do once we know a state of stress. Now we just have to figure out what cases we actually can calculate a state of stress in the first place, you know. So let's take a 10-minute break and start at 2 o'clock, and I'm going to talk a little bit more about tensile tests, and then we'll go on to this next topic. Yep.
The 0.77, so, I mean, would it be wrong to think of it like, we figured out the normals, right, and all that stuff, like, so, you know, like, what's the furthest from going out, right, 45 degrees,
Yeah.
right? So that's the magnitude of which, the further you get the strongest shear strength in that object.
It doesn't totally, it doesn't totally. Okay, anybody have any questions before I go on to the last part of this whole intro so far to this class has just been understanding what stresses are, how you transform them from coordinate system to coordinate system, how you relate stress and strain. And we have one more topic, and then we're going to use that in all the rest of the stuff, but then we're going to move on to the entire rest of the class, which is just figuring out what the stress is when you load a beam like this and whatever. Anybody have any questions about principal stresses, what we've been talking about? Okay, so the last thing I want to talk about before we move on is tensile tests. We talked about, so tensile tests are how you calculate the Young's modulus and the Poisson's ratio. But I want to talk about what happens if you use a tensile test to do a graph of the stress versus strain as you go all the way from the material being unloaded to the point where it breaks in two pieces. Okay? So imagine that you set up a test like this. There's your sample material. And you clamp the top. And then you, little by little, pull these apart. With some tensile force F. And say that at each instant, you calculate the stress, and let's say we're using the x-axis along the axis of the sample in the loading axis. And so at each instant, we're calculating the xx stress, and let's say we're also calculating the xx strain. And the question is, what does the stress XX versus strain XX graph look like? And this will give us a little information about material behavior once you get past that limited region that we're considering in this class. So as the sample goes from unloaded to broken in two. So we'll put the XX stress on the y-axis and the XX strain on the x-axis. And the graph starts out like this. So the first part is really boring. Here's the origin. I'll call this point A. And as we go from the origin to A, you can see there's a linear relationship between stress and strain. This is the linear elastic region. And all the calculations that we're doing in this class are related to this region of the stress strain curve. So this is the region that concerns us in this class, the region of the graph. That this class is about. So it's a line because of the linear relationship between stress strain. Since this is still an elastic region, that means that if you let go, if one of those clamps slipped off or if you stopped loading it, no matter where you are along this line, that sample will return basically instantly back to its original shape. Okay? And we're talking about very small strains, you know, like 1 times 10 to the minus 4 or something. I should say not every material has a linear elastic region. Well, not every material has an elastic region at all. And not every material has this linear relationship between stress and strain. But engineering materials do in general. All metals do. And so for a lot of things that we care about, this is a reasonable assumption that the graph is going to look like this. Even a lot of things that aren't engineering materials have this. Bone has a linear region like this. Bone's pretty brittle compared to most metals, so it's small. But for that small amount of deformation, you still have linear elasticity. Okay, so after that, you lose that linearity. So the graph starts to do this. After A, two things happen. The material no longer has a linear relationship between stress and strain. And the deformation becomes plastic. Plastic deformation means if you unload it, it doesn't go back to its original shape anymore. There's some permanent deformation. Now there is something else that we have to start considering when these deformations get big. When we're dealing with these tiny deformations, strains of 10 to the minus 4 and stuff like that, as this sample stretches, remember, it gets longer and thinner. That's an exaggerated picture, but it gets longer because you're stretching it, and it gets thinner because of the Poisson's effect. But we still calculate stress by taking the total force applied and dividing it by the cross-sectional area of the undeformed shape. Okay? Can you picture what I mean? Like as this thing deforms, that cross-sectional area is changing, right? It's getting smaller. But that change in area is so small, you might as well just keep using the undeformed cross-sectional area. But as these deformations keep getting bigger, there starts to be a noticeable difference between the stress you would calculate using the undeformed cross-sectional area and the stress you would calculate using the current deformed area. Okay? So as the deformation increases, there starts to be, you begin to see a difference between the stress, okay, so the stress is equal to force over cross-sectional area. There begins to be a difference, I didn't spell that right, between stress equals force over area using the reference area, or let's say the original area, the original cross-section area, and the stress equals force over area using the current cross-sectional area. So this becomes more pronounced as the cross-sectional area continues to decrease. So now there's a couple of different ways this stress-strain curve can look. If you calculate the stress as the force divided by the original cross-sectional area, that's called the engineering stress. And if you calculate that stress based on keeping current measurements of that cross-sectional area, so that's F over A current, that's called the true stress. And they start to look like this. So in the black line, I'm going to do the engineering stress. And in a dotted line, I'm going to show what you get if you measure the true stress at every one of those locations. And the end of both of these is where the material breaks in two. It's very loud when that happens. It's not really very relevant to anything here, but just something that I will never forget. It's very surprising when it happens, especially if it's not supposed to happen in the experiment you're doing. Okay, so in either one of these, so notice qualitatively these look sort of the same. You have the linear elastic region. Then you have something, and in this linear elastic region, there's one more thing I wanted to say. The slope of that region, anybody know can anyone figure out what that slope would give you? Yeah, very good. The slope in the linear elastic region is Young's modulus. So the steeper that slope is, the stiffer the material is. Once you get to that plastic region, the material is getting less stiff. You can see that the instantaneous slope gets lower and lower, right? And it would sort of make sense that the material after you get into these big deformations, that you would start to get that the material would start to get softer, more flimsy, more compliant. But there's actually this weird thing that happens. After you stretch it a little more, it starts to get stiff again. It's strange, but it's called strain hardening. So call that point B. Call this point C. From B to C is the region of strain hardening. And you can see that the slope that's dropped down starts to increase again. The material starts becoming stiffer again now that you've stretched it a certain amount. I'm sure there's a chemical reason for that or whatever, but I don't know what it is. And then finally at point C, the material breaks in two. That's not how you spell that kind of two. That's fracture or failure. Okay, so I think that's kind of a description of what happens in a very simple loading pattern, all the things that happen to the material as you go. It's important to remember that this is us. This is all we're dealing with, that linear elastic region. Okay.
Does this apply, like this type of thing applies to any type of, when I say type, I mean the shape of a, let's say, a bar? I know in this class we're just going to be dealing with a straight rectangular bar, but what if that bar was, initially was like an arc form? Is this still going to apply to that, or is that
Well, this is just looking at strains, stresses and strains, axial stresses and strains, and so the different shape of the bar would affect what kind of stresses and strains you have in the material for a certain kind of load, but this is applicable for the axial stress and axial strain no matter what the shape of the material is. This is just looking at a single point, you know, with a certain kind of stress. So yes. Okay. I guess there is one more thing that I want to say before we go on to calculating actual stresses of materials under loads. This is sort of a key concept for the rest of the class. It's called St. Venant's principle. St. V-E-N-A-N-T. Ooh, how do you spell this kind of principle? L-E, very good. And this has to do with the fact that our hand calculations, the techniques that we're using, only apply to very simple types of loads. So we can only do calculations for simple loading types. Loading types, like uniform distributed loads. And in reality, that almost never happens, that you have the loads applied in the way that we're going to apply them. So the question is, to what degree are our assumptions about like uniform distributed loads applicable in cases where loads are applied at points or non-uniform distributed loads and things like that? So that usually doesn't really occur. So where will our hand calculations be valid? Okay, so an example of what I'm talking about is we'll be dealing with cases like this. This is our assumption. The real load might be something like this. You have that same material, but you're basically applying a point load at the ends. When are these equivalent? And St. Venant's principle says, St. Venant's principle. Measure the largest dimension on the loaded face. So in this case, if this is if this has a circular cross section, the largest dimension on the loaded face would be the diameter of that cross section. If this was a rectangular cross section, then the largest dimension would be the diagonal. Okay, so measure that largest dimension on the loaded face. You can replace the actually occurring loads with equipolant loads and get good results. As long as you're at least, okay, so measure the largest dimension, let me call that lowercase l, okay? So you measure that loaded face, the largest dimension, call that L. So you can treat this point load as a uniform distributed load as long as you're at least L from the loaded face. So what that says is, in this example up here, we're not going to deal with what's happening at the ends. We're going to ignore regions like this, near where the loads occur. But in all of this, our results are valid. Yeah. So if you did two experiments with identical beams and you applied a uniform distributed load on one and a point load like this on the other, there would be big differences between the stresses and strains that you would get in this red region. This one would have a big deformation near that point load, you know, all sorts of weird stuff going on near that point load. But once you get at least the distance L away from the end,
Mm-hmm.
the loads in here are going to match.
And what is that distance L? Is that the face, the largest face that you're pulling on?
So if that cross section is, a circle, okay, then this is L. But this isn't some kind of mathematically provable thing. It's an observed rule of thumb that we can take advantage of. So what if this is like, what if your loaded face is like the shape of a dollar sign, you know? Like, what do you measure to figure out the longest, who knows, you know? Just roughly, it's like measure from one tip to the other tip. Make sure there aren't any obvious ways that you can measure it longer. Get about that far away from the end, and your results are fairly good. That's
So if you had a rectangular bar across the diagonal, or
yeah,
square bar.
that's right.
Okay.
Yep. But even that, I think, might be taking this like mathematically a little too literally. You know what I mean? It basically, I think the way to take it is just like, don't trust your results too close to the end, but once you get a ways away from the end, your results will be good.
Would we have to have something to
Right. Yep.
say,
So
well,
that's the rule of thumb. Yeah. Exactly. Yep. Oh, I know. I wanted to say this one other thing too. Before I do that, any other questions about St. Venant's principle? It's really lucky it works this way, because if it didn't, I mean, if changing the way so say you apply 5,000 newtons of tension to this body. If changing the way you applied that 5,000 newtons of tension affected all of the stresses noticeably all the way through the material, there'd be no benefit to doing hand calculations, you know. One cool example I forgot to mention. So I told you how to calculate. The stress tensor that contains the maximum shear stress, right? And the way you do that, so the stress tensor containing the maximum shear stress is in a coordinate system rotated 45 degrees from the principal coordinate system, right? And the more brittle a material is, the more important the maximum shear stress is for determining when it's going to break. The more brittle a material is, the more completely it breaks due to shear. So shear stress contributes to fracture more the more brittle the material is. And the way that shows itself is in brittle materials. When they break in compression or tension, the fracture pattern always occurs at a 45-degree angle from the loading axis. So it always occurs along a face, rotated 45 degrees from the loading axis. One example is compression fractures in the leg. Like when people get into car accidents and their foot hits the back of hits the front underneath the dashboard, and you get bone fractures from that compression. It looks just like this. Bone is a really brittle material, and so if that's your tibia or your femur, the fracture looks like that. It's at an almost perfect 45 degrees from the loading that happens like this. And that's because it occurs along the face where the stress due to that compression produces the greatest value of shear stress. It's pretty interesting. And so like doctors, they can tell, so if you go into a trauma surgeon or whatever, and they look at the x-ray and it looks like this, then they know how that fracture happened. You know, when people are looking at like car injuries or whatever, they can tell how that bone was broken based on the way it fractured. Okay, any questions about any of this? Let's stop, and then tomorrow we'll get into tomorrow is the start of the rest of your class. We'll start talking about under specific patterns of loading, specific shapes of materials, how can you figure out what the stress is here and here and here?
Are you going to post